well, there it is. So in today's lecture, we zoom back in on the center of our solar system. 2 weeks ago, Dr. Müller told us about ways to explore our solar system and explained us what knowledge there is to gain about our sun. This week, Professor Keller will tell us what is already known about our sun. So yeah, we will learn more about what Dr. Müller was actually investigating. Like said before, this week's speaker is Christoph Keller. He's a professor of experimental astrophysics here in Leiden, and he has done a lot of research, which he will tell you about. So have fun.
Good afternoon, good morning, good evening, wherever you are. It's a great pleasure for me to give this lecture here. Up front, I have done solar physics myself for about 20 years, but about 10 years ago, I changed to searching and characterizing exoplanets. So look for twins of our own solar system. So what I will talk about today is the sun, a general overview of the sun also as our star. And I will do this by giving you an overview first of what I'll talk about. I'll talk about the solar atmosphere and the solar interior. I'll talk about the sun in time, how it evolved and will evolve. Then we'll do a little break of a few minutes. And then I'll continue with the sun as a magnetic star, magnetic fields on the sun. I'll talk about space weather, and I'll finish with the solar cycle. So why is the sun such a unique star for us? Well, first of all, very simply, it is the closest star. It takes about 8 minutes for light to go from the sun to the Earth. If you compare this to the closest star, light takes about 4 years to get there. So that's how close we are. And because we're so close, it is the only star where we can really look at details on its surface, in its atmosphere. We can do that with light. We can also do it with X-rays, radio waves. All of these are electromagnetic waves, as we call them. But we can also measure particles. We can measure electrons, helium cores, all kinds of things that come from the sun we can measure directly, something we cannot do for another star. And then we can also look inside the star. And in particularly for the sun, we can do this really well. And that allows us to figure out how the sun is built up, test our theories about stars. We can do this with something that's called helioseismology. It's similar to seismology on Earth, where you use earthquakes. We use sunquakes to study the inside of the sun. And there's also something we can do, which are called neutrinos. These are very special particles that we can measure that come from the sun. And I'll talk about that more later on. And while maybe trivial, it's sometimes good to remember that the sun is the only star that is of importance for life on Earth. If you turn off the sun, we would freeze to death here right away. So it is fundamental for understanding our life on Earth to actually understand the sun, our main energy source. So let me start with a few numbers just to give you an idea of how the sun compares, how big it is, and so on. So the radius of the sun is about 100 times more than the radius or diameter of the Earth. So you could fit 100 Earths along inside the sun until you would go from one edge to the other one. You need to take about 300,000 Earths to get the mass of the sun. So it's much, much heavier than the Earth. The surface temperature is about 6,000 degrees Celsius. And even tungsten, a metal that is very difficult to evaporate, even tungsten evaporates. There is nothing known to us that would not evaporate at this temperature. When you look at the surface of the sun, so the part that you see with your naked eyes, the density there of the gas is only about 1/100%. of what we have here in the air that we're all breathing. So the layers that we see of the sun are not very dense. In terms of composition, the sun is made mostly out of hydrogen, with about a third being helium, and then 2% is the rest. And that includes things like carbon and iron and other elements. The inside of the sun becomes very hot. If you go to the very core where you have nuclear fusion going that produces all this energy, we have a core temperature of about 15.6 million degrees. Incredibly hot. And it's also very dense in there. You have about 150 grams per cubic centimeter. That's about 8 times the density of gold. Or if you take a big shoebox, then you very quickly get to the weight of a car. So very, very dense, very, very hot. That's why you can have nuclear fusion. The age of the sun is the same as the one of the Earth, and we know that very well. It's 4.57 billion years. And remember, a billion in English is a milliard in Dutch, so it's a billion is 1,000 millions. So the Earth is the same age as the sun, and we're about 5 billion years old. We now also know from looking at exoplanets that planets form almost at the same time as a star. They form shortly, within a few millions after a star has been formed. So the first part of my lecture here will be on the solar atmosphere and interior. What you see in the background is the McMath Pierce Solar Telescope on Kitt Peak in the US. For about half a century, it was the largest solar telescope in the world. It has a primary mirror diameter of 1.5 meters. And when I worked there, I was in charge of that telescope. If we want to understand how the sun works and how it looks on the inside, we can start at the very center. You see that here at the bottom, and then we'll go out radially from there all the way to the edge of the solar system. So if we start at the very center of the Earth, the innermost part, we have what we call the core. In the core, that's where the density temperature is high enough that we can do nuclear fusion. So hydrogen is burned into helium through a nuclear reaction. And actually every second, 700 million tons of hydrogen are converted into helium, and the energy that is set free by that then slowly goes through the sun. It takes about 30 million years to reach the surface, and then it makes visible light, and that's what we see here on Earth. On top of that core is something that we call the radiative zone. In there, energy goes via radiation. Basically, you can think of very extreme X-rays that slowly bring the energy throughout about 70% of the solar radius. And then on top of that, you have the convection zone. In the convection zone, the energy is transported by gas flowing, hot gas flowing to the top, cooling off, coming down. It's the same thing that you have when you boil soup, where you also see these cells of material, hot water, hot soup streaming up. The same thing happens in the sun. And then at the very top of this convection zone, we have what is called the photosphere. The photosphere is that layer of the sun that we can actually see with our eyes. It's very thin. It's only a few hundred kilometers thick. On top of that, we have the chromosphere. The chromosphere is something that we can see with telescopes and special filters. And then even further out, we have the corona, a very hot part of the atmosphere that is heated by magnetic fields. It again goes up to 10 million degrees in heat. And that one we can see either during an eclipse or particularly well with satellites. And so this is what we call the atmosphere. On top of that, we have the solar wind. The solar wind is a constant stream of particles that leaves the sun and goes through the whole solar system. So all the planets are inside the solar wind. Let's start with the photosphere. Among the first ones to actually look at the sun with a telescope was Galileo Galilei. And he made drawings, and you can see one drawing here on the left. And he already recognized that, yes, there are sunspots. The surface of the sun is not beautiful and clean, but it is immaculate. It actually has spots. And while Galileo couldn't do that yet, we can now take his drawings and make them into a movie. So what you see here are drawings made by Galileo assembled as a movie. And what you can see from that right away is that the sun actually rotates. It rotates around in about 25 days. And you can also see that the sunspots appear in about 2 belts. They all seem to be in about 2 areas. They're not at the poles. They're not at the equator. And you can also see that these spots are not stationary. They change over time. So as soon as people started to put a telescope on the sun and look at it, they saw a lot of details. These days, of course, we can take much better pictures. Indeed, satellites now continuously take pictures of the sun. What you see here is the sun 2 weeks ago, and I can now start this as a movie, and I'll show you the sun, how it looks like over the last 2 weeks and then 2 days ago. You can see sunspots here. You see how these sunspots move around, they evolve. Sometimes suddenly one comes up and goes out, they drift apart. And you might also notice that there is a flickering in the background. Very, very small things seem to flicker. That's not because of compression or the transmission that you have, but this is really coming from the sun. And we can understand what that is by looking more closely at the sun. To do this here, I'm going to show you images from the largest solar telescope that just started taking its first pictures. This is the Daniel K. Inouye Solar Telescope in Hawaii. It has a 4-meter diameter mirror, so a very large mirror, and it can take very, very sharp images of the sun. Here you see not just an image, but you see a small detail of the sun over about 20 minutes or so. And what you see is, like you see the soup boiling, you see these convection cells. You see they have bright centers in the interior where hot material comes up. It cools off at the surface and it flows down as dark gas in these dark lanes in between. On the top left, you also see a globe here, the Earth. So you have a little bit an idea of the size that you see. If you look at the very smallest details on this image here, then you notice that it's about the size of the Netherlands or even smaller that we can detect now. Indeed, in the very center, you see very, very small, very bright features. These are actually all due to magnetic fields. And one can show that when you have magnetic fields, you can see deeper into the sun, and there it is brighter. And that's why these magnetic fields show up as these small, very bright structures. When we go up from that, we look at the chromosphere. The chromosphere is something that you can see, for example, during an eclipse. If you look at the edge here of this picture from the last big eclipse, you see these red areas, prominences as we call them, that come out. They're red because this is hydrogen that you see glow, and glowing hydrogen glows in red. And that's what you see here. So that is the layer right above the photosphere. You can also see this with special filters where you only look at the light of hydrogen, and that's what you see on the right. This is with our own Dutch Open Telescope on the Canary Islands. And what the movie here does is it starts with the image in the photosphere at the lowest level, and then we go more and more into hydrogen. And the last picture is right smack in the middle of hydrogen. And there you see a very, very different structure, a lot of filaments, a lot of extended objects here. And these are all basically formed by magnetic fields. And then when we still look at an eclipse, what you see on the left, you see what we call the corona. Of course, corona has a bad term these days, but this is what it used to be. It's the large structure around the sun that you see, beautiful filamentary things. You see hair sticking out. You see loops that go back in. You can see this beautifully with your own eyes during a solar eclipse. But these days, we can also use satellites, and there we look at extreme ultraviolet and X-ray radiation, as you see on the right, and that picks up only very hot material. The photosphere does not glow at all in X-rays, that's why it's dark, but the corona above is somewhere 1 million to 10 million degrees hot. That emits X-rays, and if we look at the sun in X-rays, we actually see the corona. And so these days we can look at the corona all the time from satellites, not from the ground, because the atmosphere absorbs this radiation. And then on top of that, we have the solar wind. On the left here, you see old measurements of the speed of the solar wind and its direction. And you see that close to the pole, this wind comes out at a speed of about 700 to 800 kilometers per second. And then closer to the equator, where you have more magnetic fields, the speed is typically less. It's only a few hundred kilometers per second. On the right, you see measurements of Voyager 2. Voyager 2 was a mission to the big gas planets, Jupiter, Saturn, Uranus, Neptune, and it has long left the major planets of our own solar system. It actually reached by now more than 3 times the distance between the sun and Pluto. And if you look at the measurements of what happens when it measures the particles, just about good 2 years ago, everything started dropping. The solar wind particles started dropping, and radiation from the galaxy started to pick up. That's when Voyager hit the edge of the bubble of the solar wind. And the solar wind pushes against the material between the stars, and that's, you could think of a little bit like the edge of the solar wind, or the furthest part that the sun really goes. So that's where we are right now when we go very far away. Let's turn this around and go on the inside. We cannot see directly the inside of the sun. There's no radiation that we can see directly. But what we can do is use seismology. So similar to what you do on Earth, where you measure the shaking of the ground to learn more about the inside of the Earth, we can do the same thing. What you see here is a picture that shows the speed of gas over the sun. And I can now start this as a movie. I'll let this play here. And what you see is, like in the background, you see there is something going up and down all the time. And what this is really the sun ringing like a bell. But a bell has typically maybe one tone that it can play. It turns out if you take a big sphere of gas like the sun, it will play about 10 million tones at the same time. And they all add, and that's what you see, this flickering in the background. These are all these tones, all these frequencies wavelengths showing up here as oscillations. The interesting thing is that why does the sun ring like a bell? It is because we have this convection. We have these cells at the top where matter flows, cools off, and goes down. And when the matter goes down, it really goes down fast. And at some point, it hits gas and just gives it a big shock. And so it's like when you do seismology on Earth, where you use a big truck to basically hammer on the Earth. These convective motions hammer on the surface of the sun and make the sun ring like a bell. We can use measurements like these here to infer what's on the inside of the sun. What have we learned with this? Well, we have learned how deep these convective motions go, about 30% of the solar radius. We learn about the temperature. We can learn about the composition, how much helium is there at what depths in the solar atmosphere. And what is really interesting, we can also figure out how the sun rotates as a function of depth. And what you see on the right here is like a speed map. Red one means rotates in about 25 days once around. And if you look at the blue dark areas, those rotate maybe with a period of about 34 days, so much slower. So what you see is that the sun rotates much faster at the equator. And when you go to the very inside, everything becomes yellow. So at the innermost part, it rotates like a fixed ball. But further out, it rotates much more like a cylinder, where the outermost parts rotate much faster than the innermost parts. And so that's important to remember when we look at and try to understand the solar sunspot cycle. Another fascinating thing you can do is you can forecast where sunspots will appear. On the left, you see an image that was created from measuring the velocities at the surface and extrapolating from that what gas is doing 60,000 kilometers down. And there you see something going on in the middle. But if you look at the surface, which is on the right side here, you see absolutely nothing. But 2 days later, this is how the same thing looks like. Not much at the bottom at 60,000 kilometers depth, but at the surface, a sunspot has emerged. So we can now basically have some idea when a big sunspot will appear, and we can do that in advance. We can do also very fancy things where we can actually use these ringing bell effects to see sunspots on the backside of the sun that we can't look at. So a lot of things you can do with helioseismology. If we go to the very core, I wanted to explain a little bit how the sun actually generates its energy. We start with two helium cores or protons. So it's just the atomic nucleus of a hydrogen atom. We take two of those and we push them together in a very hot area, and they combine, and out of that comes what we call a heavy hydrogen. So it's hydrogen, but there is a neutron added, the red particle here. But in addition to that, we also get a positron. It is the antimatter of an electron. That positron combines with electron and also creates energy. You know that from Star Trek, if you combine antimatter with matter, yes, you get a lot of energy free and nothing is left over afterwards. Same thing happens to that positron. In addition, you get a neutrino. A neutrino is a particle that basically almost does not interact with any matter. So they are produced in the core of the sun, and they speed right through the sun. They could go almost through a light year of lead. There's so little that they do with anything else. And you know what? If you hold up one finger and you look at your fingernail, there are about 100 billion neutrinos going through your fingernail every second. And they all come from this nuclear fusion reaction in the core of the sun. We don't notice anything because they just go through. There's no worries with them. And then we add another hydrogen atom. We combine them again. And out of that comes now a helium core. It is a light helium. It only has one neutron. So to make the real helium, we need to do a little bit more. This reaction doesn't create any other particles, but it does create light. It does create what we call a photon, like very, very high energy X-ray that then slowly makes its way through the surface, cools off, and comes out at the top. If we now take two of these light helium-3 cores, we can combine them, and out of that comes now regular helium core, which has 2 neutrons and 2 protons. The helium is a little bit lighter than the 4 hydrogen atoms that we started with, and that energy, according to Einstein's E equals mc squared, is made into energy. And so that's the basic reaction that happens in the sun, and it burns hydrogen into helium, and out of that we see the neutrinos that come out directly. Now, if you do the math here, you'll also see that 2 hydrogen atoms again come free. We added 6 in total, we get 2 back, so there are really 4 hydrogen atoms involved to make the helium. Now, to measure neutrinos, which would show us directly what's going on in the inside of the sun, that's actually a tricky thing to do. What you see here is the Super Kamiokande detector. 50,000 tons of very pure water surrounded by a lot of detectors, and these detectors see flashes when neutrinos very once in a while interact with the electrons in the water. To give you an idea of how big this is, I'll make a circle here around. This is 2 technicians in a rubber boat servicing one of these detectors. Huge installation, and you need so much water because it is such a rare case that a neutrino actually reacts with an electron and creates a flash of light. Nevertheless, out of that, they were able to make an image of the sun seen by neutrinos. So this is using these huge detectors over 500 days and measuring for the neutrinos that they saw where they came from, and they make that into an image. And so here you actually see the solar core imaged from the Earth in neutrinos. It is very difficult to judge how good this an image is. This is actually a very wide angle image. Here is the equivalent image with an optical lens. The sun is a very small thing in the sky here. The fact that the sun looks so big here is simply because we cannot determine the origin, where in the sky the neutrinos come from very well. And so it's a very fuzzy image of the sun. Nevertheless, all of this told us that there is nuclear fusion. The neutrinos come out. It told us about the temperature, told us about the composition in the core, and confirmed our theoretical models. In the beginning, it was very interesting because people only measured a third of the neutrinos that they expected. And for a long time, people were not clear what it was. Is our understanding of the sun wrong? It turns out it was our understanding of neutrinos was wrong. And now we understand why we see less neutrinos. It is because they transfer into another kind of neutrinos while they go through the sun. And that leads us then to not correct them. There's several Nobel Prizes that came out of that. It's a really fascinating part of science. Let me switch now and look at the temporal aspect, how the sun evolved over time. The sun is now good 4.5 billion years old. Nothing fancy there. If we go back to the beginning and we start at the very start, we see that the sun, our models all predict that the sun only had about 70% of its current luminosity. So it was dimmer. It was colder at the surface, and it was smaller. And we also know that young stars have very strong magnetic fields, a lot of changes in the magnetic fields, and it had a very strong solar wind. We think that it rotated in about 9 days as compared to about a month. So much faster rotation. And the interesting question now is, how could life on Earth evolve when the sun was dimmer? It was less warm, we got less solar energy. Very interesting aspect how that interacts with greenhouse gases in our own Earth's atmosphere and how things evolved over time. If we look into the future now, I'm going to show between now and 8 billion years from now. Right now, we have used up about half the hydrogen in the core. So you can say we're about half time. And now we're starting to use up more and more hydrogen. So over time, over the next 3.5 billion years, we're starting to use up the hydrogen. The sun keeps increasing in brightness, so this will give us some problems here, but 3.5 billion years is a long, long time from now. Earth will become probably more like Venus because we have higher irradiance. And then if we go to 6.5 million years, really the hydrogen has been used up, but we still have hydrogen in the outer layers outside of the core, so that starts to undergo fusion reactions. The sun will be about 60% larger and will be about twice as bright. And then when we go to 7.5 billion years, the sun suddenly expands massively, 150 times larger than its current size. You can imagine that up to the Earth, pretty much everything will be swallowed. At the same time, it will get cooler. And because it is so big, it is actually 2,500 times brighter than what it is right now. So a red giant. And then at about 8,000 million years, all helium has been, all hydrogen has been used up, and the star starts to fuse helium into carbon. And at the same time, you have basically an explosion. About a third of the solar mass will be spit out with a huge explosion and forms what we call a planetary nebula. And on the inside of the sun, it compresses into a white dwarf. A white dwarf is a star where it's very highly compressed, but it's not heavy enough to build a neutron star or a black hole. And so that white dwarf, if you take a teaspoon of that, it weighs as much as a big car. So incredibly dense. And this is how it looks if you look from the outside. This is a Hubble Space Telescope image of NGC 2392, also known as Eskimo Nebula. It's a planetary nebula. You see the white dwarf in the center. And I know these online lectures can be quite taxing. And so we'll do a 3-minute break here. That gives you time to get some tea, some coffee, stretch your legs, and then I'll continue in 3 minutes from now. Okay, I hope everyone had a chance to get some refreshments, stretch legs, ready for the second part. I think I'll have to go a little bit faster looking at the time here. So here is the sun as a magnetic star. This is now the inside of this 4-meter DKIS telescope that can take these fabulously sharp images of the sun. And just to give you an idea of how big this telescope is, I'm showing you here 2 people with their hard hats on. Huge solar telescope, takes magnificent data. I was lucky enough to be involved in this at the beginning. Looking forward to a lot more images coming from there. Now, going to the sun as a magnetic star. On the left side here, you see again the sun about 2 weeks ago, and just like we would see it with our eyes. On the right side, you see what we call a magnetogram. This is a map of the magnetic field on the solar surface. And we can observe this continuously with satellites. And you see now the last 2 weeks how this looked like as a magnetic map. The way that we measure magnetic fields on the sun is done with what's called the Zeeman effect. This was discovered by Peter Zeeman in Leiden in 1896, and he got the Nobel Prize for that. And we use this all the time to measure magnetic fields in astronomy. If we look at an image in more details, you start to see there is a magnetic field basically everywhere. We can zoom into this map here, and you see there is signal basically everywhere. If we take a bigger telescope, do more measurements, we always see magnetic fields everywhere. So the whole sun is magnetic, but obviously in some parts the field is a lot stronger than in other parts. We can also look at the corona. Here is an image in X-rays of the corona at the edge of the sun, and you see these beautiful loops. And that, of course, reminds us immediately of the loops that iron filings make when you put a magnet close to them. Magnetic lines are always close, so they tend to form loops. And so this also tells us there is something going on here with magnetic fields. The most prominent type of magnetic field on the sun is a sunspot. Here is a movie made with our own Dutch Open Telescope in the Canary Islands. And you see how you see the convection on the outside, and the sunspot looks very differently. If you measure the magnetic field inside the sunspot, it's about 10,000 times stronger than the Earth's magnetic field. Indeed, the magnetic field is so strong that it can keep all this convective motion, all this boiling. It stops it. It doesn't let that motion happen anymore. And that's why a sunspot looks so dark. Another aspect I want to cover is space weather. So there's actually weather in space. What you see here is a telescope that I actually designed and developed and built with a team. And here is just after we installed it at the test location. This is the Solis VSM. I'll show you some data from that in a minute. Where does space weather come from? Well, the most well-known reason for it is flares. I'll show you here a movie in extreme ultraviolet, and you see suddenly there is this strong brightening just above the center, and a second later or so you see all this snow on the detector. Again, this is not zoom giving you problems, but this is actually radiation that hits the satellite just about 8 minutes after the flare went off. So this is X-rays, gamma rays that hit the detector and that you see here. Flares occur when you have very complicated magnetic fields on the sun become unstable. That's about the best we can describe it right now. And they release a tremendous amount of energy. So a flare that you see here on the left, that's the equivalent of 10 million of the largest nuclear bombs that have ever been constructed. It's a huge amount of energy that gets released within a very short time. That energy makes also particles accelerate towards the Earth. And unfortunately, we don't understand these too well. We have some ideas of what's happening, but we're still at a point where it is difficult to predict when a flare will go off. The flares have a lot of impact on Earth, and so predicting them is one of the big challenges of solar physics. In addition to flares, we also have what's called coronal mass ejections. If we make a coronagraph, that is an instrument that does not show coronavirus measurements as a function of time, but it actually makes an artificial solar eclipse, like you see here. This again shows the same flare that I showed you before. And you see that all that mass that gets thrown out of the sun is what we call a coronal mass ejection. Again, the detector gets hit by the radiation. Basically, a whole part of the corona is thrown out. It does that with a speed of about 2 million kilometers per hour. So you'll get a fairly hefty fine if you drive like this. Since the Earth is about 150 million kilometers away from the Earth, you can calculate it takes about 75 hours to reach the Earth. So this is a few days and it reaches the Earth. In terms of the mass, it's like 20 billion tons of gas that is thrown at us. And that is equivalent, like if you take the Veluwe, cut it off at sea level and take all that mass and just throw it at us. That's a single big coronal mass ejection. These CMEs, they also happen without a flare. There's something unstable, doesn't make a flare, but it still creates a solar mass ejection. And of course, not all of them will hit Earth. It's only those that are really directed towards Earth. What happens if we look at Earth now? What you see here is a simulation of the Earth. This red, orange, yellow is the solar wind and the pressure that it creates. And the gray veil that flatters in this solar wind, that is a calculation of how the Earth's magnetic field will look like. And what you see is that when you have this mass thrown against the Earth's magnetic field, it changes the Earth's magnetic field. And many of the problems that we have is actually coming from these changes. On the lower right, you see a simultaneous image of the poles of the Earth, and you see aurorae, northern lights on there. What are the impacts on Earth that we have from this space weather? Well, these particles can hit satellites and just destroy them. So it happens once in a while that a satellite just gets taken out by it. It can be a danger to astronauts. It is okay, they can deal with it if they're close in within the Earth's magnetic field. But if you're on the moon, for example, you get into quite some trouble. The X-rays that come at the same time, they change the charge in the Earth's atmosphere, and they can lead to radio blackouts that disturb GPS signals. Suddenly you're not driving on the road anymore where you thought you were driving. And if you have a big flare, it actually can destroy part of the ozone layer. And you can measure this for weeks afterwards that there was a flare that did that. As you have seen before, the Earth's magnetic field changes, but it also, to some degree, prevents and protects us from this. So what we have on Earth is largely that the Earth's magnetic field is changed. But you know, probably from the dynamo on your bike, when you move magnetic fields, when you change them, they make electric currents. And these electric currents, they can actually go into the power lines that we have. And so basically they can create an overload. This is the transformer before. This is the transformer afterwards. This was a $10 million transformer at a nuclear power plant that was taken out by an event where the magnetic field changed so much. It actually left 6 million people in Canada without power for 9 hours. So there's quite some impact from space weather, and that's why if you Google around, you'll see that there's a lot of interest in space weather because we rely so much on technologies. A much more beautiful impact are northern lights. Here you see a movie taken from the space station, the green light. This is all from northern lights from aurora. It's when some particles hit the solar magnetic fields, went along the magnetic field lines, came down close to the poles, and created these beautiful displays of light. You can also see these on other planets. Here is an aurora on Jupiter, and you also see one here on Saturn. So and that's because solar winds, coronal mass ejections, they all go far out in our solar system. I'd like to finish here and talk about the solar cycle. When you look at the sun at 2 different days, here on the left you see one in 2000, on the right one in 2009. The sun can look very different. On the left you see a lot of sunspots, on the right you see no sunspots at all. And so indeed the sun does change in the number of sunspots. And this is a graph that shows the number of sunspots since the discovery of the telescope to pretty much about today. You can see when Galileo saw sunspots, there were obviously quite some sunspots. And then you see from 1650 to about 1700, basically no sunspots at all. And for a long time, people thought, well, these were probably some dark ages in Europe. People didn't look at the sun. Nope, not true. There were basically no sunspots, and that's what we call the Maunder minimum. There are other ways to look for this, and it's very clear. And the other thing, of course, you can see from this is that every 11 years, there's a maximum in the number of sunspots, and then about 5-6 years later, there is a minimum. And the cycles vary in strength. You see that the last few cycles have not been as prominent as the one in the 1960s. So the strength of the solar cycle also varies massively, all the way to not working at all. We see this also in a lot of other solar observations, of course, because a lot of things depend on the magnetic field. You see on the left in a solar minimum, on the right in a solar maximum, and extreme ultraviolet, much more activity and change, very little when you're in the minimum. And then, of course, we can look directly at the magnetic field. You ask yourself, how does the magnetic field look like? And here's a movie illustrating a little bit how we look at this. These are maps of the magnetic field of the sun as it rotates. And then you can use that to make a map of the sun, like you have maps of the Earth. And I'm showing these maps here for every solar rotation. So you see we're starting to get to the 1990s, very strong magnetic field, maximum, slowing down, going to a minimum, almost nothing left, and then building up on the next cycle, magnetic field is coming up again. You see that you have these 2 belts here. And we can take this map now and we collapse it to a single line, and then we show all these lines. And this is what this is showing here. So this is an illustration of magnetic fields on the sun as a function of latitude, so from South Pole to North Pole, and how it evolves over time in the horizontal up to about now. And the interesting thing that you can see is that there's actually a magnetic field at the pole. And when we don't see many sunspots, there's actually a lot of magnetic field at the solar poles. And if we now go 11 years later, you see that the sign of the magnetic field has changed. So the sun flips its magnetic field every 11 years. So this cycle that we see has to do with flipping the field. The Earth does something similar, but fortunately it takes a lot more time. It's something like 100,000 years or so. We're still trying to understand this. We have some ideas of how this happens. Here is an example of an explanation how this looks like. What we start here with is at solar minimum, we have polar fields. Magnetic field comes out, goes into the sun at the South Pole, comes out at the North Pole. And now, if you remember back when we talked about the solar rotation, it rotates a lot faster at the equator than it does at the poles. And that means these magnetic fields get wound up. And it actually turns out that they get wound up so much that they basically become horizontal. And you can also show that at the same time, the magnetic field must increase in strength dramatically. At some point, the magnetic field gets so strong that the sun cannot hold it on the inside, and it breaks out, it comes out. And when magnetic fields come out, there's something called the Coriolis force that twists them. It is exactly the same thing that happens on the Earth when you have hurricanes. This is air flowing out, and because of the Coriolis force, it gets to twist. And that's why hurricanes are actually like spirals. And they actually change their direction if you go to the southern hemisphere. Same thing happens on the sun. The fields get twisted. So one pole is closer, one magnetic field is closer to the pole, the other one is closer to the equator. And that means that towards the equator, the opposing magnetic fields, they start to cancel each other. But what we still have left is at the poles. And so in the end, what we're left up with is a magnetic field that's again only at the pole. Everything at the equator and everywhere else has canceled. And if you look at it, we have actually exactly the opposite direction now. So that's one way to understand why there's a sunspot cycle, why there are magnetic fields at the pole when we have no sunspots, and why the magnetic field flips. That also means that space weather has an 11-year cycle, and you can see this in a number of things. One of them is the space telescope, the Hubble Space Telescope. If you plot its height above the Earth's surface as a function of time here since it was launched, it generally declines. Sometimes it goes up, like here and here, but those were actually space shuttle missions where they took the Hubble Space Telescope and moved it back higher up. And what does this do? Well, I'm plotting here the sunspots. And you can see when we have a lot of sunspots, like here or here, then it drops much more quickly in altitude. And that's because the radiation from the sun expands the Earth's atmosphere. And so there's more atmosphere even at 600 kilometers altitude. That means there's more aerodynamic resistance, and that means things start to come down. When you have a big flare, satellites can actually drop by a few kilometers. And so you sometimes can't find them after a big flare. It takes a few days to find them again. Also, solar arrays degrade when they get hit by these particles. There's another thing that varies with 11 years. You may know the solar constant, that is the amount of energy that we receive at Earth per square meter. And these days we can measure this very accurately from satellites. And you see here these measurements. It is not a constant, it is variable. It is very tiny changes, only a fraction of a percent that it changes. But the interesting thing is when you plot at the same time the number of sunspots, you see that at the time when we have more sunspots, we actually get more energy from the sun. And you would say, well, that cannot be. If we have all these dark parts on the sun, how can it be that we get more energy? It should be the other way around. And that's something I worked on myself and figured out. It is very interesting. If you look here at an image of the sun in light as we see it with our eyes, I boosted the contrast here, then you see on the right side, close to the edge, you see something that is brighter. That's what we call faculae, or little lights basically. And if we now show the same location with a magnetic field map from an instrument I built, you see at the same place where you have these brightenings, you have magnetic fields. It's not spots, but it's magnetic fields that make it bright. Over time, we were able to look at them with bigger telescopes, and you see actually these are very small bright dots here that then together form these larger areas of brightness. And the reason for that we figured out is that in magnetic fields, we see a little bit deeper here. And when it is close to the edge, we look at it under an angle, we see into hot material, and that's what makes it lighter. And the interesting thing is that, of course, you have more magnetic fields in general, not just more sunspots. And this effect actually more than compensates for the energy that we lose from sunspots. So what's coming up in solar physics? It's very exciting times because we have a lot of new telescopes and instruments. There is NASA's Parker Solar Probe that goes very close. It actually goes into the corona in the end. It has a heat shield that you see on top to withstand this. And it's an incredibly exciting mission where you basically almost go into the sun and measure it directly. Then there is a solar orbiter from ESA, the European Space Agency. Many of you will have heard that from Daniel Müller's talk. That one will go higher up so we can look at the poles of the sun from fairly close up. And then we have the DKIS telescope in Hawaii that makes these fabulously sharp images. And in Europe, we're working on the EST, the European Solar Telescope, which also has 4 meters diameter that will allow us to do some other things with also very high resolution. This will have a special secondary mirror that is being developed by TNO in the Netherlands right now. And then we have something else. Look at this fabulous image of a sunspot. But you know what? This is a pure simulation. So by now we have the knowledge and the understanding and the computing capacity to actually simulate these things and check that we understand all of the physics that's in here. This is an image created by Matthias Rempel in the US, a wonderful way to understand with simulation and theory. And that brings me to the end. These are stamps that either have come out or will shortly come out in the US from the US Postal Service that shows all these fabulous images as stamps. Thank you very much for your attention, and I'll be happy to answer questions.
Well, yeah, thank you a lot as well. I enjoyed it very much, and I think I'm not just speaking for myself when I say that. Before we go to the questions, Shravia will send the link to the feedback thing, the survey in the chat. So if you want to have feedback on anything, you can do it there. Or if you just enjoy filling these kind of things in, you can do it. She will also send the donation link in the chat and the sign up link for next week. So, well, we can go to the questions now.
Okay, cool. We have a lot of questions, of which the first one is, on the visible surface of the sun, is the temperature 5800 degrees Kelvin? If we go further from the sun, how can it be that the temperature increases to 3 million degrees?
Very good question. That has indeed been a long-standing problem, particularly because the second law of thermodynamics tells us that something that's 6,000 kelvins hot cannot make anything that is hotter. In the meantime, we know that this is due to magnetic fields. All these magnetic fields, they shake, they move, they combine, they cancel each other, and that energy gets released in terms of heat in the end. And that's how things are getting so hot higher up. So it's a non-thermal process. It goes through magnetic fields.
How can it be that the solar wind is moving quicker from the sun?
Good question. The acceleration of the solar wind is an interesting question. What Eugene Parker, after whom the Parker Solar Probe is named, figured out over 50 years ago was that actually from fairly simple physical arguments, you can show that if you have a hot corona, that you need to have a wind. And actually that wind has to go supersonic. So the fact that there was a solar wind was predicted well before we could even measure it or before it was discovered. There were hints at it because we can see comets where the tail goes away from the sun. The ion tail, right, goes straight away from the sun. And that gave an indication that there's something blowing. But the fact that it goes and that it accelerates, comes out of fairly simple physical arguments. What it does not explain is how the energy goes into that to do that. And that's why we have the Parker Solar Probe that will go into those layers where the solar wind is being accelerated. And so we hope to figure it out then.
The inner part of the sun rotates as a solid body. How do we know the radius where this occurs?
That is through helioseismology. So we look at the sunquakes at the surface of the sun, and we can measure how they move, the frequencies, how the frequencies are related, the amplitudes, and that allows us to make a model of how the inside looks like. And so with helioseismology, we can go about halfway into the sun. So that goes through the convection into the radiative zone. But pretty much where the sun starts to rotate that is a solid body, anything on the inside we can actually not see. So we don't know whether that continues.
How did Galileo observe the sun with a telescope? Because if you do this with an ordinary telescope, you get blinded by the light, right? Did he have like a kind of sunglasses?
Correct. One has to be very careful when one observes the sun with a telescope. We used to say you can do it with your own eyes twice. A really bad joke. I know somebody who by accident did it as a kid, and yeah, that eye was not in good shape. A very simple way to do it is simply to project it onto a white piece of paper. So for example, you take binoculars and then you can actually make an image, somewhere 1 meter or 2 meters away. You get with just putting a white paper. You can also get specialized foil, mylar foil that has a metal layer on top. You may know, for example, there are these rescue foils, these aluminum foil-like things that they hand out in disasters. They're actually slightly transparent, and so you can use a number of layers of those. But it's best to either to do the projection or buy a professional filter to be sure that your eyes are not damaged.
What exactly causes sunspots?
So sunspots occur when you have a lot of strong magnetic fields. And we know from physics that when you have a hot gas, then it can only move along the magnetic field. It cannot go across. And when you think about this convection that moves heat to the outside of the sun, to the photosphere, it goes up, cools off, goes to the side, and falls down again. While in the sunspot, it can move up or down, but it cannot go to the side. If it can only go up or down, it will always not know which way to go. And so that basically stops the energy flow, and that's why it gets dark. So sunspots are simply bundles of very strong magnetic fields.
I thought that the low energy neutrinos from the sun cannot be seen by the super Kamiokande.
Correct. That's a detail that I did not want to go into. There's another experiment, the Sudbury system in Canada, and they were actually able to measure those directly. And that what gave a Nobel Prize, I think, in 2015 for that measurement. So it is correct that the Super-Kamiokande measures neutrinos from a fusion reaction that is more rare, but produces higher energy neutrinos that can more easily be measured.
125 Kelvin colder surface seems only a little less than today, especially seeing the time scale 125 Kelvin seems very little different. How come it was only 125 Kelvin lower than compared to today, and what can you say about the accuracy of this number?
It refers to the accuracy of the number. Of course, nobody was around to measure it, right? So what the way we know that is through models. And these stellar models and how stars evolve over time, they are checked on a very large number of different stars. So we're feeling fairly certain. These models are actually also used when we try to make a model of today's sun. We actually start with the beginning, let it evolve over 4.5 billion years, and then compare it to what we have now. And so the fact that stars get hotter, get a little bigger, get brighter, that is something that we know and we can measure with other stars. We can compare different stars at different ages, and we know that fairly well. Yes, 125 Kelvin may not look that much, but you have to remember that the energy goes with the fourth power of the temperature. And so a little change in temperature does actually a lot in terms of the energy that comes out.
Are photons only produced in the second stage of the hydrogen fusion process?
Yes, of course, you remember I showed this positron that is released. If you do the explanation a little bit more carefully, then there are also electrons from the hydrogen. The positron and the electron will combine, and they will also create two photons. So there are actually photons already created indirectly at that very first stage.
Why do only some neutrinos interact with electrons and not all of them?
We know that electrons and neutrinos, they come in three different flavors. So for electrons, we also have muons and tau particles. They're like very heavy, unstable cousins or siblings of the electron. And similarly, we have the same thing with neutrinos. They're electron neutrinos, muon neutrinos, and tau neutrinos. And particle physics teaches us that only electron neutrinos can interact with electrons. And so what happens is, also explains the solar neutrino problem. And the third is that electron neutrinos are generated inside the sun during the fusion process. But by the time they travel to the Earth, they have actually evolved. And by the time we reach the Earth, we have a mix of all three types of neutrinos, but we only measure electron neutrinos. And so that explains why we measured almost exactly a third less, or only a third of the neutrinos that we should have measured.
The energy in the radiation zone takes a long time to reach the convection zone. I heard it took 100,000 years, but you mentioned 10 million years. What is the mechanism of this transfer of energy?
So it's the mechanism is radiative transfer. What happens is that when you have a photon, so the particle that describes one quantum of light, it is very dense on the solar inside. So it gets created and it doesn't get far. It gets basically by the next few atoms, it will be absorbed again. It heats those up and they will emit another one, but the photon can go in any direction. So it is like a random walk where the photon slowly tries to find its way out. So it doesn't go in a direct path. And it is that random walk that takes so long. It's relatively easy to calculate from a very big picture view how long that takes. And we have lengthy arguments whether it's now how long that exactly is, but it's somewhere around 10 million years. So another way to look at it is, let's turn off fusion on the inside of the sun. How long would it take for us to notice on the outside? It would be a long time because there's still so many photons coming.
Sunspots look dark because of magnetic field. Does it mean that magnetic field line acts as a lid, being parallel to the surface?
It is almost like that. The magnetic field lines are actually perpendicular, so they go radially out of the sun in a sunspot. The magnetic field does something like also like an additional pressure, and so that keeps that on its own and keeps it vertical. But the fact is, when you want these convective motions, you always need to make a cycle. You need a closed loop. And so, yeah, you can go up or you can go down along the magnetic field lines, but you can never cross them. And that's what basically interrupts this convective cycle and makes it cool down. The energy cannot be transported from the inside anymore.
Were the Apollo moon astronauts in danger? This is in relation to solar winds and such.
Yes. So astronauts are at risk when they're in the space station, low Earth orbit. They're still within the magnetic field of the sun, so it's not that bad. But they still, when there is a big storm coming, they need to go into part of the space station that is more shielded. However, once you're outside of the Earth's magnetic field regime, so like flying to the moon or Mars, then you can easily be in trouble. And so that's why back in the 60s, a lot of solar telescopes were built, partially paid by NASA, partially also paid by the military. And one telescope that I worked with and we replaced, that was paid by NASA, and we even had NASA people on site, because for the moon landings, they needed to be able to predict something. And so they were lucky in 69, nothing happened. And certainly going inside a metallic structure helps a lot already. But when you think about the future on the moon, then you will need to have heavily shielded areas. People talk about going underground on Mars or the moon to avoid radiation problems. If you're into sci-fi, then the For All Mankind series has a very nice event like that. I don't want to give you any spoilers here, but yes, it's an issue.
What was the reason there were no or only a few sunspots between 1650 and 1700?
I wish I would know. I think many of my colleagues would wish they would know. We see that also on other stars, that these cycles are not constant. So something changes, something breaks down or doesn't happen. So this whole dynamo is still a very difficult question. Why is it 11 years? Very difficult to answer. Why does it stop? Why does it start? If you want to Google around, you can look for predictions. People predict how large the next sunspot cycle will be, and it ranges from everything from stopping to being massive. And that just shows you how we really don't understand this.
What about astronauts that will travel to and from Mars in the future? How can you protect them during the mission and the vessel they're traveling in?
Yes, that is an issue, and the best thing is put matter. You know, I'm not sure what they want to do. There are options that he would put water around them, you know, make water tanks that are on the outside. You can add metal, that helps a lot too. It's not a problem that you cannot overcome, but it is a substantial issue. Even when the Concorde flew, because it's higher in the atmosphere, to go supersonic, the pilots actually had to wear radiation detectors.
Let's see, these are all not questions. Magnetism is said to be restricted for metals iron, nickel, and cobalt. Regarding to this, how can magnetism and the sun be explained?
So the sun is a gas. It's all gas, but because it is so hot, it is also what we call ionized. So the energy is so high that some of the electrons come free. So it is, in terms of electrical properties, it becomes more like an electrical conductor, like a metal, because you have electrons, they can travel free. And it turns out the sun is actually a very good conductor. Electric currents can flow very easily. Now, it is correct that just based on that, you would not yet expect magnetism. And indeed, if you would put a magnetic field on the sun and would just leave it alone, it would disappear within a few million years. It would go completely away. But because you have motions on the sun, and because the gas is conducting, you can show that it has to drag the magnetic field along. So if you have an ionized gas and you move it, then the magnetic field that is in it has to move too. This moving of magnetic field makes currents. We know that from Maxwell's equations, and currents in turn produce magnetic fields again. So there's the constant churning and motion that you have in the sun, the rotation of the sun, that dynamically creates magnetic field. These are not static magnetic fields, they would disappear, but they're dynamic magnetic fields. And that's how we can have that on the sun.
Can we or are we learning from the sun's fusion process to apply somehow in the ether on the construction in Cadarache?
It would be very handy if we could do the same thing. But unfortunately, we're not able to get the temperatures and pressures and densities that we have in the sun to work on the Earth. So in the sun, the fusion is actually very slow. Right? You would think, well, this is a nuclear bomb going off. No, it's not. Physically, very different process. If you look at the interaction that happens, it's something called the weak force. It is the same force that a neutrino has. And so the weak force is so weak that actually the chance of two hydrogen atoms making a helium atom is very, very, very rare. And it is because that it is so rare that a star lives so long, that a star like the sun can live 10 billion years. So it is a very, very slow fusion process that goes over the weak force. We can't do that on Earth. We need to do the strong force. And that means we cannot start just with hydrogen and make helium. We need to use something that reacts with a strong force. So physically, very different process. And that's why we cannot really learn anything from the sun. If we learn anything from the sun, then it has to do with magnetic fields. Because in a fusion reactor, the only way to keep that very hot material in a place is with magnetic fields. Anything made out of matter would be vaporized right away. And so that's why on Earth, you actually need 100 million degrees to get any fusion reaction going. But the pressure doesn't have to be as high. The density is not as high. So what we can learn from is probably how the magnetic fields work on the sun. That may give us some ideas on stability of magnetic fields that we need for fusion reactions, but not from the actual fusion reaction itself, which is very different.
Okay, cool. I think that's about it. We don't have any more questions from the audience.
Okay, well, then I would like to end this lecture. Thank you all for coming, and hopefully we'll see you next week when Dr. Melissa McClure will talk about how our solar system came to be. So, thank you all for coming.